Let's look at our next optimization problem. So we're going to look at this example. A manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce a box with maximum volume? Well, let's start by drawing a picture of this box. So we're told that it has a square base. Okay, so here's my box. And then my base is square, so this side is x, this side is x. And then we have a height h. So what are we trying to here maximize? We're trying to maximize the volume of this, which is length times width times height, so it'll be x squared times h. And then we have to describe our constraint. So if you look back in the problem, you can see our constraint is the surface area. So we need to calculate the surface area here. Well, this is an open box, so we just need to calculate the area of the base, the bottom of the box, plus the area of the four sides. This box doesn't have a top, so it's just made up of the bottom and the four sides. So in the end, I'm told that this is 108. What's the area of the bottom? Well, the bottom's a square, so the area is x squared. And each side, what's the area of each side? It's x times h. It's a rectangle, and there are 4 of them, so it's 4x times h. So this is our constraint equation down here. So if you look at your constraint equation, we can solve for h. Solve for h here in this equation. So let's do that. You'll get 108 minus x squared equals 4xh. So if I solve for h, you're going to get h equals 108 minus x squared over 4x. And now you're going to take this and plug it into your volume equation. So remember, volume was x squared h. So now plug in for h. Volume will be x squared, 108 minus x squared over 4x. And if you distribute, you're going to get volume equals, and if you simplify, you'll get 27x minus x cubed over 4. So here's the function that we're trying to remember. We're trying to maximize, and I've got it down now where v is just a function of x. So before we find our critical numbers, we should stop and think about what is the domain of v. Well, your box could have no volume. It's made up of just a base. And what's the maximum x could be? Well, the maximum is that you use all of your building material for the base. And so the height would be 0. So if the height is 0, look at your equation. 108 equals x squared if h is 0. So x, the largest it can be is 100 and square root of 108. So now we're going to find the critical numbers in this interval, So take your derivative of v with respect to x, dv dx. It'll be 27 minus 3x squared over 4. That's always defined, so just got to set it equal to 0. So you get 27 equals 3x squared over 4. So if you cross multiply, you'll get 3x squared equals 108. X squared equals 36. X equals plus or minus 6. Now it doesn't make sense for x to be negative 6. Remember, we're looking at this interval here, and negative 6 is outside of it, so we're going to toss out negative 6. Now, I found my critical number, but I need to know that this is actually going to give me a maximum. So to do that, we're going to look at our sign chart. We said 0 to square root of 108, and here's 6 on here. Pick some test numbers. If I test out 1 into my derivative here, you'll see that it's positive. If I test out a number larger than 6, like 10, you'll see that the derivative is negative. And so think about it, your function is increasing and then decreasing. This is a relative maximum. So x equals 6 corresponds to a maximum. What does that mean the dimensions of my box are? Well, you got to go back to your h equation. $108. Oh. So go back to your h equation. It was 108 minus x squared over 4x. If you plug in 6, you should get 3 for the height. So the dimensions of the box that produce the maximum volume are 6 inches by 6 inches by 3 inches. And that will give you a box with the surface area will be 108 square inches, and we will have maximized the volume.